Hello, everyone. I know it's the last talk of the day, so everybody's really tired and excited for the after hours party thing. But yeah, bear me with this last talk. And I know we've had a lot of interesting talks with coroutines, memory leaks, and a lot of interesting stuff we understood about Jetpack, a lot of interesting things. But today, what I'm going to talk about is a research project showcase that uses Android behind the scenes. It's a lot less about like advanced tooling, but more about how we try to piece together some things to create this project. So VizInteract is the name of this research project that our lab initiated. It was to create an interactive data visualization experience, and that was using an Android canvas behind the scenes and another Android-related tool that I'm going to talk about a little later. But we're trying to create this large-screen data visualization tool. So let's talk a little bit about myself. The way I'm connected with Android is I started off my career as an Android developer for 2 years, then switched to UX design, and then now I'm studying HCI. So basically a person with really less attention span. So I have, I like to delve into Android as my side project passion, and I do some things with Android, but yeah, nothing as advanced as you guys are doing in your production level or day-to-day code. About my community presence, I organize the Google Developer Group for my city, and I'm also the ambassador for Sketch official group. Last self-plug is that I have this podcast that I'm hosting, which is talking about research papers that are relevant for your day-to-day development and design job. So if you're interested in research papers that have significance in industry, make sure you give a listen to that. Talking about the supervisor of this project and the lab, so Wolfgang Sturzlinger is the professor at School of Interactive Arts and Technology, and he's the one who spearheaded this project. So he's kind of like a mentor and a guide. And he's worked extensively on interactive data visualization experiences. So yeah, I was, I think, in good hands. So being part of this research lab, a grad lab, you get tons of toys to play around with. So this is one of the prime attractions of our lab. What this is an 8-panel setup of 4K displays that are synced, running off one computer and running at 60 hertz refresh rate, and they're synced. And it was the sort of the environment to showcase our visualization tool called DinSpace, which is more of like, if anybody's used Tableau, Excel, anything like that, it's more like Windows, mouse, and keyboard-based approach. So it was geared towards that. So the next motivation that we had was, how do we create an interactive data visualization tool for touch-enabled displays, because we also had touch panels for these displays in our lab, and we wanted to use multi-touch gestures for all kinds of data exploration. So the question is, why Android? We wanted to ask, like, the first question that comes up is, we definitely wanted to support a lot of different device configurations, going from like your phone to a tablet to extremely large screen. And the fundamental goal was to support VA tasks, like visual analytics tasks, on lower-end devices. So that was key for us. So I'll just go a little, I'll show a simple demo of what VizInteract is. You have this place. Okay, yeah. So you see you have a canvas on your right, and what you have is you have your dimensions of the data on your left. You bring them onto the canvas, drag them, you can rotate them, can move them around. 2 different configurations that we support, more rotation configurations are to be planned. So what happens if you bring 2 different oriented visualizations together is you create an overlapping scatter plot out of these 2 visualizations. So this is a frequency histogram when combined gives you a scatter plot. And you'll see the interesting thing is, if I bring in 2 similarly oriented visualizations, you create a parallel coordinate plot. And if you long press on it, you can filter down the data visualization. You can do extensive operations on it. And similarly, the neatest thing that you can do is you can bring in as many visualizations as you want, and you can chain them. You can create this whole multi-dimensional data exploration experience. So yeah, this is what VizInteract is. And I'd like to showcase what we tried to achieve this and where we failed in the first place. The first thing that we tried was using all the popular charting libraries that are for Android. Like, I'm pretty sure if you've made any kind of statistical display in your app, you've probably used one of these libraries. But the problem with these libraries is, even though they're so extensible, so powerful, you have so many different types of visualizations supported on these. The major requirement was that we wanted a graceful transformation from one view to another. We really wanted to go from that simple histogram view to a scatter plot to a parallel coordinate. So we really wanted really graceful transformation from one view type to another. So that didn't work. We also tried D3.js in a web view wrapped in an Android app. But the biggest problem was performance, and we had a significant decrease in performance when we were using multi-touch gestures with multiple graphs on screen. So a big no to using any kind of visualization library in a web view and use it for your app. So our simple structure for the app turned out to be just using a simple canvas. We call it the graph surface, but it's basically a canvas housed in a surface view. And we have a data manager that talks to this surface view using a surface holder. And there's a gesture detector that sits in between the canvas and also the visualizations that are supported and rendered on the screen. So that's a basic architecture. There's nothing fancy. I'm not using any really over-the-top configuration here, but this does the job for us. So coming to the learnings and sort of understandings about Android Canvas that I found using this was, first and foremost is canvas transformations, save and restore are your friend. Like, canvas transformations and save and restore, these are essential if you really want to work with Android Canvas because they let you be sane and work with drawing routines in a much more simpler manner. And I'll just, like, a simple refresher on Android Canvas save and restore is that, say if you had to draw this figure on screen and it's all upright, it's standard location, what you would do is you would just have a simple drawing routine for making it, like making those shapes. But if in the same case, if you had your figure all inverted upside down and it's like towards the top right, how would you go about achieving to draw this? One way is you could probably just start going directly printing it the way it is, rendering it the way it is, but the easier way would be to first have a blank canvas, save your state, so canvas save would help you do that. You rotate the canvas, and then you shift your origin to the point where you want to start drawing, and then reuse your drawing Android code, and then restore the canvas back. So this whole process allows you to be a lot more manageable with entire drawing routine. So canvas save and restore definitely is something important. And yeah, they also need to be balanced. This is a problem that I ran into because if in your app you're trying to defer the rendering to different classes, you have multiple view types that are taking care of rendering their own drawing routines, save and restore balance becomes sort of a mess. You need to make sure that you're balancing every save call with a restore call. And things that you can help you achieve this is, like, you can use some of these helper methods like get save count and restore to count, which can help you be a little bit more manageable with your code. Now, get save count basically returns the difference in the number of save calls and number of restore calls. So if you're getting 0, so that's a good place to start. That's a good place in your code because you're balancing those calls. And if you want to pop back to a certain save state in your save and restore stack, you would just use restore to count, and you give a number, and you just pops back to the appropriate save stage. So that's also helpful. The important thing to remember is popping back the canvas save and restore stack is not actually removing any of the drawing. The drawing still stays. You have to make sure that you're just keeping that in mind, because it's not going to remove any of the drawing code that you have. It's just going to undo the transformations and modifications you did to the canvas transformation matrix. So yeah, I'm going to come to that later. But if you did want to make an undo operation, which our app also has, VizInteract has an undo operations, what we do is we keep a running log of entire transformations on the canvas, including additions and deletions. So these are things that we keep in our app, and that helps us to programmatically go back to any state we want. The other way, which is a little more memory like intensive, is you could keep a list of, and those who are seeing like non-Kotlin code, I'm not someone who's moved on to Kotlin, so this is all going to be like old Java style code, so please bear with me. So the other way you could do this is also keep a list of like last 5 bitmaps of the entire canvas. It's going to be a little bit more memory intensive, but you could keep like a limit of 4 or 5 bitmaps of the entire canvas and keep them in a list, and as soon as user initiates an undo operation, you pop them and showcase it to the canvas. So yeah, I keep talking about this transformation aspect of canvas. So the basics ops that are supported on the transformation matrix are scale, translate, and rotate. That's all well and good and helps you achieve what you want on a basic level. But if you want to get the matrix and you want to modify it on your own, the earlier method before Android 16 was just do a canvas.getMatrix and you have the matrix with you. But post Android 16, there's been an issue. If you have hardware acceleration enabled for your app, it's not going to work. And this is a dated knowledge, but it still is relevant because sometimes you'll do a get matrix thinking that you're getting the right consistent matrix, but it's not. It's because of this bug. So we did this, this is an overhead that we added, but I think it does the job for us. We maintained a parallel transformation matrix. Like we maintained an entire matrix which just replicated what we're trying to do on the canvas, and it kept that transformation on a separate matrix. I would not advise you to do that. There's another neater way that I found is that if you take the canvas's parent view and you get the transformation matrix from that, it's going to be consistent and it's not going to have that issue of not accommodating for the status bar. Like there's a bug, I can give you a link to that issue on Android issue tracker, but yeah, you can use parent view to get the right matrix. So this is probably the best way to do it. Now, transformation operations will often lead you to the point where you have to accommodate for a local coordinate system and a world coordinate system. What this means is, say you're between and canvas save and restore cycles, like you're in between and you're trying to do some computation. You'll see the coordinate system shifts, and the coordinate system is not exactly the true representation of the physical device screen. So what you have to do is sometimes you'll have to map points between these systems. And say you've made some operations on the matrix, the thing that you can use is you can use a map points helper function that just takes in a world coordinate array, and it just transforms it back to a local coordinate system, and it just writes it on the array that you have. It just gives you the local coordinates. So extremely important if you're doing any kind of mapping points work. One thing which I've found, this is just from like simple testing, there's no like stress testing that I've done for this, but what I've found is if you have a transformation matrix and you apply operations on it like translate, rotate, and scale, and then you draw on the canvas bitmap using that matrix, it's a little less, slower compared to what you can just directly do canvas.translate, canvas.scale. These are faster, and I haven't really found out what the reason is for this, but we can talk about it. If I'm wrong, please let me know. I mean, if people have worked and found that they're same, that's one thing that that's one thing I've found through development of this app. Now, imagine if you had a lot of operations and you want to combine them into one matrix and apply it to the canvas. The one way you could do it is use canvas.concat, which allows you to just multiply any given matrix to your canvas matrix. And the important word here is like concat. Why it's concat? Because you're trying to multiply something to a specified matrix. And if you know, like matrix multiplication is not commutative, so it's not like A into B is not B into A. So that's why it's important that you understand what you're applying as a transformation to your canvas. So a canvas scale dip, and I think this is multiple times you'll find into Stack Overflow that people keep pointing this as an issue, is that if you have a scaling operation and you also have a hit detection logic, you want to detect some object being interacted by the user on the canvas, you'll run into this problem that you're thinking the event is just not being detected because your coordinates are not, you think your coordinates lie within the object bounds, but it's not. So what you're trying to do is you miss the aspect of accommodating for the scale factor and the clip bounds of the local coordinates. So if ever you're thinking that your hit logic is not working, that's because you haven't accounted for the scale factor and the local coordinates clip bounds. So what it does is you'll have your touch event X and Y position, and you'll divide by the scale factor to get the zoomed in or zoomed out values, and then you'll add the clip bounds of your current local canvas to get the true X and Y. So if ever you fail on the hit detection logic, just make sure this is something that you haven't accounted for. So this is all between canvas save and restore. A quick quality of life thing that I added to my app was using a region object behind my shapes. So if you use a region object, you have these very quick, helpful methods to do a quick contains and quick reject. What this allows you to do is just find if two regions are intersecting, overlapping, or you have a point that is contained in that region or not. So this was helpful for us because we have a lot of proximity-based logic that we're trying to use for our visualizations. Talking about scaling, if your app is not hardware, if your app has hardware acceleration, if you're using hardware acceleration on your in your views, you should use the canvas draw bitmap and then supply the scale matrix to it because it's GPU accelerated. But if you're using bitmap.create bitmap and then passing in the scale matrix to it, you're basically using a CPU-based resizing operation. So keep that in mind if you want to allow for hardware acceleration. This, I guess a lot of people, if you've ever worked with Canvas, you would know, or rather any graphics libraries that in your draw and render cycles avoid creating, or avoid, like it's a strict no that you should not initialize any objects, decode any resources in your draw or render function. And I learned it the hard way because we introduced this color logic in our scatter plots, and I was seeing that the performance really degraded all of a sudden. What was the reason? The reason was I was doing a color.parse in my draw function, and that was the reason which was causing the jankiness. So defer all of that to some initialization function that if you can use. In my case, I also have some histogram-related logic that I use in the init functions of each of these visualizations. This is the smartest thing that you can do is if you have a lot of smart, like simple shapes, simple rectangles, simple closed paths, what you can do is you can create a path and just add all of these rectangles, ovals, and shapes to that path and render it one time. Like this is a one-shot rendering versus having multiple render loops for each of your shapes. So it's important that you make use of this, and this helps if you have simple repeating patterns and shapes. Data processing, this was one of the things which I didn't know much about, and then I had to refactor a lot to introduce this, is I was doing a lot of the data stuff because it's a research project. I don't have to exactly adhere to a lot of the best coding practices, but I was finding that the experience turned out to be really poor, and I did have to think about a way of introducing data processing and sourcing on another thread. So the simplest way is you could have a surface view which has callbacks to your surface holder, and you get the surface holder in your surface view, you pass it on to your data thread, whatever data processing thread you have. And then what you can do is in your thread you have an ability in the run function. You can just get you can lock the canvas and do all of your drawing routines on the canvas and then unlock it for the other threads. One thing I've noticed is that the locking, like the amount of lock time varies. It's not a standard lock time for like mid-range devices. You will sometimes have like 9 milliseconds, 10 milliseconds of locking time. So that's one of the things that I found. But for the second part of the project, which I'm going to talk about, is it didn't matter a lot, but yeah, just keep this in mind that the locking times can vary. Surface holder. This is another interesting tip that I have is if you have bitmaps being rendered to your on your surface view, make sure that the surface holder format matches the bitmaps format. So if you are using a 16-bit bitmap, make sure that same format is also applied to your surface holder. And avoid transparency formats as much as you can, because transparency is always a double render cycle. It always takes a little bit more computation power to do any kind of alpha computation. So make sure the format for your surface holder is matching with the bitmap. So you can use set format, and it takes in a constant from the pixel format class, I think. That's it. Just that. And this is random. I didn't find a place to put this slide in, so I just thought of putting this here. Is that if your text looks bad, just make sure anti-aliasing flag is enabled for your paint. And this was like coming from design, I was like, this looks garbage. So it's like it's one addition that you can do, but you can still you'll still be not meeting the crispness of let's say a simple text view that you have in your UI widgets, but it does get close. So yeah, now coming to the second part of the project, which was how do I get this stuff onto the large interactive display. The setup was like this. We had an 80-inch 4K panel and from Samsung, and we had this infrared-based touch overlay that we had from a company called PQ Labs. So we were trying to find a method to use this and run Android on it somehow to eventually run our app on it. I mean, the first question that somebody could ask is that, I mean, why not use Android emulator on a Windows OS and just show it on that large screen? But the problem with that is that, first of all, the multi-touch works, but it works only after you press a modifier key. Like you have to press down Command or Control, and then you'll get those handles. But it's not as great. We wanted a much more direct manipulation approach. Like, can you directly manipulate things on screen? So yeah, that was a setup that we had, and we thought of ways to do this. And the first method, like the first research if you do on how to run Android on a traditional off-the-shelf Intel or AMD-based box, is that there's a project called Android x86. What it does is it's an AOSP derivative, but it has some patches put in to just support Intel and AMD CPU architectures. So we wanted to run Android off of like a regular desktop computer. So that was one of the reasons, because we had to drive that large display. The first thing that I actually did was like I took Android x86 and I wanted to experiment it at a much smaller scale. Like I wanted to use a smaller prototype for it. So I got this like another toy in our lab. It was a 24-inch touchscreen monitor, but it was manufactured by 3M. And I just took this monitor, connected it to the box, and had a live bootable USB image of that Android x86 OS. Plugged it in, and it just works. So there's like, the app also works, and I was like super excited. Okay, now this is like, I just made my life a lot easier. But I was wrong. So I took the same setup, I plugged it into my actual large screen display, and it doesn't work. Like the input touch system doesn't work. Like the touch input was completely like non-responsive. So what I found out was that 3M is a very popular touchscreen frame manufacturer. They're really big, and they have their drivers in the Linux upstream. So Android x86 just naturally gets support for it. So plug and play definitely works there. So then I ventured into this sort of dark world of like, how do you come up with a kernel module hack for supporting PQ Labs IR overlay? So a lot of digging. I mean, this took so long to find that there's some engineer by the name Gemini who had written a 1-point touch frame driver for Linux 2.6.3, like way back. So I was thinking, okay, I have something in hand, like I have that driver, and what I did was I cross-referenced the 3M touchscreen driver for Linux, and then I started playing around with it, and what can I change? And believe me, if you've never done like kernel compiling and debugging, I mean, it's not as simple as log.d, it's not. It's a whole different world. At least there's, I mean, to me, who's coming first time into this, was like completely a new thing. What I found was a little bit of research. I found that some of the things that matter is the product ID, vendor ID is something that you have to get you have to know from the USB maintainer before you start making the driver. So I reached out to PQ Labs. I was like, can I get a hold of this? And like, I also found that they had some driver made, but it was not publicly available, and they would not disclose it to me. So otherwise, I would have taken the driver from them and just used it in my project, but sad luck there. And the next thing was how do you support multiple touch points? So if ever you get a chance to like do some device driver configuration and you think what's a good place to start, the probe function in a device driver is usually the place where all of the configurations are set up. So make sure you get into the probe function and see what you can figure out from there. What I found that I had to tell the input subsystem that I wanted to support more than 1 points, and this is how you do it. You add another constant, max support points. In this case, it was 32 touch points for my app. I know this is a lot of stuff that nobody cares about, but the important thing here is that I basically cross-referenced the Multitouch driver for 3M and found that there were other variables that I had to set for my systems to work. Like, apart from the X and Y coordinates of your touch events, you actually need a lot more other configurations, which includes things like position X, position Y, orientation, a lot of other stuff, which frankly, I'm not even sure a lot of those things mean. But I just found that this is something that I have to instantiate. So yeah, the amount of joy I had when I like saw those green lights come up on the screen, it's like, finally, I have like a working touch frame on the large display. And towards the end, you'll see there's a lot of delay, right? So there's like, you drag your finger, there's a lot of latency. And that was sorry, I just escaped. So the thing is, that latency needs to be fixed, and there was something that we could not live with. So I again had to go back and see how exactly do you modify these values. So the lines that I showed you earlier, they're kind of important. What I found that there's an input parameter there which is called the fuzziness value, and what this is just the amount of noise that the input subsystem can expect from a user on that touch panel, and it decides how it wants to filter those input positions based on this value. And it just has two things to it. Like, it can either not move your cursor till it reaches that difference, and it also detects like drop-off zones. So that is one of the values that we had to experiment with. I mean, most cases you can just keep it as 0, it's gonna work fine. But what we find that in our lab, we have a lot of these VR trackers that are IR based, and there was a lot of noise that, like OptiHouse trackers, if you ever use some of these VR systems, we have a lot of noise on the panel, so we could not just use the value of 0, and we experimented a lot of kernel images compiled over time, and we found that the value of 10 works. It's still not best, but the value of 10 has really helped smoothen out the latency a little bit. Apart from the device driver, what did we do on software side to accommodate for this large screen setup? I found that if you're doing any kind of velocity tracking in your app, in your canvas, if you're trying to do any kind of velocity tracking logic, if it uses it, what you'll see is that on a large screen, the velocity threshold for doing a same action is a lot lower than a smaller form factor. Like, because you have a larger distance to track, so your hands definitely take a lot longer to do the same action, even though it's the same amount of pixels. So the screen size makes a big difference. So 80 inches of screen real estate makes a big difference that you have to account for that. So make sure if you're ever doing something like this, which I'm pretty sure nobody's gonna like go home and say like, I'm gonna set up an IR-based touch panel on your regular TV and do this. But things that are important and kind of also applicable as you have your screen sizes increasing. So there's also touch jitter. Like, if you're not using a native capacitive panel inbuilt on the TV or the monitor, what you'll see is there's a lot of touch jitter. Like, our panel was highly sensitive to small movements. It's like, even if you just keep your hand like this, you'll like, it's an on-move action. So what we were figuring out was that our long press events were not being detected, our filter handles were not coming up. So we found that it's just because of the way the panel is and it's set up for high sensitivity. So we just made a simple hack around it. We set up like a threshold. If you are there's an additional constraint of a wait period. If you for 300 milliseconds you're in the same zone, and that distance threshold you can find, like you can utilize the scaled touch slop. If you ever go into like input subsystems, you see that there's a minimum amount of distance that every Android or Linux-based system keeps for detecting past that value. They're going to treat it as scrolling or dragging. So you can use that value to your advantage. So that was how we figured out that we can still make do with this jitter. Accommodating for scaling while rotating. This is another problem that you'll run into, is that when you think you're rotating, your angles, definitely like your angle between the pointers that you're using for the touch event, the angles are definitely changing, but you in fact also move your hand. And this is much apparent in a large screen. You'll see that you end up also scaling. So the scaling is something that also happens alongside rotation. So just to make it feel a little bit more natural, what we did was in our rotation gesture detector, we also accommodated for scaling. So anytime you'll see your angle is lesser than a threshold and your span between the two pointer indices are more than a certain value, you can just treat it as a perceived scaling operation. So all of these minor performance improvements are like important because in our research project, we were especially doing a lot of rotation scaling, which are computationally intensive processes in graphics in any way. So any kind of gains can help. And yeah, like things like, double buffering, if you've played with graphics before, it's like you render to a buffer and then you can do all of your scaling and one-time operations, transformations to that buffer and directly present it. These are good, but for us, didn't mean, like this meant doing it twice. The computational drawing cycles will be doubled. So we just dropped it trying to meet that 60 FPS goal. Also, things like, the primitive count, if you want to be under that, if you do a GPU profiling on of your apps, you'll see that if you reach 400 primitive counts and above, you'll start losing that 60 FPS experience. So things like those are important. Just to make lives easier for anyone else who ever decides to play around with this setup, the patch for the PQ Labs driver, I have added it to the upstream of Android x86. So if you use, and the reason I'm telling you this is because the most popular external touch frame for your screens is PQ Labs. So you'll end up using their product, but if you think it's not working with Android, now it will. So just a small announcement there. So kind of like the last thing that I have to share is that this, the large screen demo that I have, like what exactly is it translating it to now? So if it just plays. Dramatic intro, by the way. Sorry about that. So, yeah. It's slowed up, I don't know why, but. So yeah, rotation is working. It's not exactly the smoothest, but yeah, we're getting there. So we create a scatter plot. We can move the scatter plot around. I'm just trying to do stuff here for like a video demo. So my acting talent is at stake. And yeah, the thing you'll notice that I'm doing like zoom operations using two hands is that I'm not able to meet that threshold using just my two fingers. So. And you'll see the effect of velocity tracking is that I'm not able to do the, like if you do your hand like this, it's not treating it correctly is because you're not meeting that velocity threshold to treat it as scrolling. So these are things that you want to keep in mind. So yeah, that's pretty much it. Like that's the demo that I had. And I know I'm a little short in time, but if you have any questions, you can always, you can ask them right now, but you can also reach out to me on Twitter or anywhere else. Or you can meet me here in the after hours thing. Yeah. Samsung. The pen. Yeah, so the question that he's asking is, who manufactured the screen and the panel is what you're saying, right? So the screen was Samsung and the panel was PQ Labs. Does that answer your question? Okay. Any other questions? Yes.
So you mentioned using regions for like computing your overlaps.
Yeah.
Was there a region for each graph?
Yeah.
Like a third region for like the dots when you overlap?
No. So the dots. Okay. All right. So I think I'm just getting the hang of this now. So the question is, did we have separate regions for each of those graph types? So the short answer, the only answer is that I had a region for all the visualization types that I had. So all the parallel coordinates, all the scatter plots, all the individual histograms, all had a region. So it made it's not exactly the right way to do it. You would probably have a better bound system, but it's a lot more logic to write, like, is it falling within this bounds or not? So we just made it a region and did a quick overlap detection using that. Any other question? Okay. Yeah, so that's pretty much it. Thank you guys for listening and have a great conference tomorrow as well.